This is Jack Jackson. In this video we're going to look at a t-test. In fact, we're going to look at this over the next several videos. And this is our first example of this. So we're going to try to go through this in some detail. So first of all, remember, just like we have a t-interval, which we've discussed in the previous videos, which we usually use instead of a z-interval for computing confidence intervals for the mean distribution, there's also a t-test, which we use instead of a z-test when performing hypothesis tests about means. Now remember, there are conditions that we need to perform any particular type of inference procedure, and you always have to check those before you start. For both the z and the t, we're performing inferences about the mean of a population. So a z-test or a t-test, at least the one sample version, we're performing a test of hypothesis comparing a sample mean to a hypothesized population mean. For both the t and the z, the distributions of sample means must be at least approximately normally distributed. And remember, we have at least sort of three cases. If the individual measurements are normal, or very nearly so, we can even get by with very small samples. And in fact, the t-test was designed for just that situation, where we had a normal distribution of individual measurements, but we were working with very small sample sizes. And number two, well, if the sample size is greater than 30, for nearly any distribution this works. If you're somewhere in between, say around 15-ish or so, then you don't have to be completely normal, but you have to be kind of free of some bad stuff. What's bad stuff? Heavily skewed, outliers, bimodal would also be a problem. So if those things are worked, so if you get even the least bit mound-shaped and free of these other things, then a pretty small sample size will work too. So how do we decide between a t and a z? Well, a z-test or z-interval requires that the population standard deviation is known, which is a condition that's not usually true. And in the t-test or t-interval, the population standard deviation sigma is unknown. So the t-test ends up being the appropriate test to use in many, many cases. So some of this we've looked at before, but let's review here. How do we adjust our methods to fix the problem that the population standard deviation is unknown? Well, of course, just like before, we simply use the sample standard deviation, S, in place of the population standard deviation, sigma. And the foundation of z-tests and z-intervals is the test statistics from samples are z-scores of sample means, and they have a sampling distribution, which is a standard normal z distribution. So if we do x bar minus mu divided by sigma over the square root of n, the sigma over the square root of n is the standard deviation of the x bars, sometimes called the standard error of the mean. This gives us a z-score, and the distribution of these z-scores are distributed normally. Not only normally, but with a standard normal, mean 0, standard deviation 1. Now, when you replace sigma by s, that is, replace the population standard deviation sigma with the sample standard deviation s, then that changes the distribution slightly, makes it a little bit more variable, and this actually, a z becomes a t. So we might call the z the standardized version of the statistic. We might call the t the studentized version, after the student's t distribution, when Gossett was using the pseudonym student whenever he worked on and developed this distribution. So anyway, this is distributed with a t distribution with n minus 1 degrees of freedom. So what we're going to do is we're going to go through and explicitly work through all the steps of a t-test, specifically a one-sample right-tailed t-test for this example. And at the end, we'll check our work with the built-in t-test app on the TI graphing calculator. So the recommended amount of sleep for an adult human is 8 hours per night. However, a student life publication of a university indicates that the average amount of sleep for college students living on its campus is 7 hours per night. A random sample of college students were surveyed to see how many hours per night how many hours of sleep they got per night. So below we see the results of that data that they collected, and we see this here. and we want to do a test of hypothesis that the students actually get less than the reported 7 hours of sleep per night. Now, one of the things that we need to do is we need to choose a significance level, which is alpha, and here we're going to use an alpha 0.1, and then here's our data. Okay, so the first thing we need to do is to maybe decide what kind of inference we need to do and check the conditions are true. Now, as I said just a minute ago, these 3 conditions must be satisfied to use a t-test, and let's check them out. We're performing hypothesis tests comparing mean of a sample against a given hypothesized mean. That's true, so that's a one-sample t-test, or that's one of the conditions. The population standard deviation is unknown. That's true. And then for the next part, we need the distribution of sample means to be approximately normal. Now, since the sample size is only 10, we need to be reasonably sure that the distribution of individuals does not deviate significantly from a normal distribution. And one way to do this is with a normal probability plot. And so the next slide we'll check on that. Sometimes we can skip the normal probability plot if we're told that the distribution is normal to begin with, or if the sample size is really large. But we can use a t-test if and only if all 3 of these conditions check out okay. So we know for sure 2 of them check out. We just have to check the normal probability plot. So what we want to do is first get our data in the calculator. We've done this several times, so I'm just going to skip to the screens here showing you this, and talk you through it real fast. So on the TI-84 screens, you see 4 of them over here on the left. You hit Stat, Edit, go to L1, put your cursor on the L1, right up there on the label itself, hit Clear and Enter. That'll clear this out. Then we type the data in, and 5.2, enter, 6.8, enter, and so forth. You get them all in there, and that takes care of that. Then we go to plot setup, which is second y equals, and then we turn on plot 1. We choose plot 1, we turn it on. We choose the last one here for a normal probability plot, and actually the rest doesn't really matter. Well, yeah, it matters that you push L1 for your list of data. You can actually switch either axes here. It's still going to give you basically the same conclusion, and you can use whatever mark you want. I typically use this. And then to get a look at the graph, do a zoom 9, which is zoom stat. You can either arrow down to the 9th one and hit enter, or if you know it's 9, you could just say press the zoom button and 9. And we get a graph here, and we see that they're reasonably close to a straight line, and so that tells us that, okay, this data is close enough to being normal that we can go ahead with a sample size of 10 and assume that our distribution of sample means is normal. Here's the same thing on a TI Inspire. First, we create a tab page that has a spreadsheet on it. I gave it a name. I typed in sleep up here, made sure this was cleared out. Again, typed in all the data in a particular column. This is column A, which I've labeled sleep. Then we make sure we add a page that's a statistics data analysis page there, and we'll see a bunch of just dots, which are these things kind of out in random order. Click on the x-axis down here and choose sleep, and all of a sudden now we get a dot plot. And we see that these are almost kind of uniformly distributed here. It's not too far off of what we might expect with this small of a sample size for a normal distribution. And then to get this plot to turn into this plot, what you do is you're still in this window up here, and you click on you click on menu, and then you look at plot type and turn it into normal probability plot, and it turns in. And if you notice, these dots are the same order as these dots over here, and also it gives you the regression line there as well, so you can get an idea how that compares to line. So either way, we can get a normal probability plot which is close enough to a straight line. We feel comfortable proceeding, and so we can assume that that's true. Now, the next thing would be to state the null and alternative hypothesis, and the null hypothesis is that mu equals 7. Actually, we're really operating under the assumption that the distribution is normal. The distribution of sample means is normal, at least. Distribution of x bars is normal, with a mean of 7. And it's that distribution that we're going to be drawing all of our probabilities from. Okay? And or a studentized version of that distribution. which we'll look at some more in a minute. The alternative hypothesis is that mu is less than 7, so it's a one-sample left-tailed test of hypothesis about the mean. So let's look here a little bit. So we're operating under the assumption that the distribution of individual measurements is normal with mean 7 hours per night. We take samples of size 10, such as this one, and compute the mean of the sample and the distribution of sample means. And it has this normal distribution with the standard deviation. Sigma sub x bar is sigma of x. Sigma of the original x is over square root of n, or just sigma over square root of n. So it's sigma over square root of 10. So that's a smaller standard deviation. If we could graph both the original distribution and then the distribution of x bars, the distribution of x bars would have the same center, but would be narrower and, of course, taller in the middle. We don't know the standard deviation of the population, so we don't really know sigma, but we do know that if we studentize the sample, in other words, find this sort of like a z-score, but not quite, then we can get this student's t statistic, and it's x bar minus mu over sigma divided by sigma over square root of n, and that's our t statistic, and the distribution of these t follows a t PDF, a t distribution. This is the PDF for it, very similar to a normal PDF. In fact, it's very similar to a standard normal. It has mean 0 and a standard deviation, not 1, but just a little bigger than 1. So it's a little shorter right in the middle, just barely, and a little fatter, a little bit more spread out than the standard normal, but otherwise pretty close to the same shape. Now let's compute some sample statistics. We could do this, by hand with the sample this small, but it's going to be a lot easier if I use a calculator. Since I've got this already typed in, I can do one variable statistics for list 1, and I get x bar is 6.5. Of course, I could have done that by just adding these up and divided by how many there are. I can just count them and see that there are 10 data values there. So n is 10. Add them up, I get 65, divided by 10, I get 6.5. The standard deviation is a little harder to compute, but we know how to do that as well if we had to do it without any kind of a shortcut like this. But since we have it available, this is the S that we're looking for. Don't use the sigma, use the S. And so I've got those 3 summary things written down here. Here's the same thing of what it looks like after you compute that on a calculator here. So the one variable statistics on the TI-84 is, let's see, it's stat, calc, and then say, L1. Calc, and then it's number 1, which is one variable statistics, and then L1. And that's what you're wanting to take the statistics of, and enter, and you get this. Similar thing here. I believe, if I remember right, it is menu, statistics, stat calculations, and I think one variable statistics is, again, the first one there. And tell it you want to do it for list 1. Tell it you have one list, and then that you want to do it for list 1, and you get this same information here. This arrow down gives you the quartiles. You can see they're here as well. All right, now what is the t statistic for this particular data? Now the mu we're assuming is the hypothesized mu that they reported of 7. Basically what we do is we assume that they're telling the truth. If we're going to call them a liar, we've got to have some data to support that, right? We're going to question their statement. The burden of proof is with us as the researcher here to investigate. Okay, so the mu is 7. The x bar for our sample is 6.5. Now certainly that 6.5 is less than 7, but the question is, how is it enough less than 7 that we think it's much more likely that the real amount of sleep is less than 7 hours, or is it just we happen to just get a sample that was a little bit low, but the real mean actually is 7? Of course, either one of the two things could happen, but which one is likely? Can we put some numbers with it, some probabilities, and that's what we're going to do here. So finish substituting in the formula. X bar is 6.5, mu is 7. The S we just computed is 0.99666, etc. And of course we know the sample size is 10. And so work all this out on a calculator, which you can see over here. And I stored it as t, and there it is, negative 1.58645792. All right, there's the t value, our test statistic. Now we have two methods to go here, just like we did with the z-test. We can do the critical value method, sometimes called the classical method, and then there's the p-value method. So we can do it by comparing critical value to t value, t star, the test statistic, or we can compute probabilities and compare them, compare alpha and the p-value, which are probabilities. Okay, so let's take a look at this. Since it's a left-tailed test, the entire critical region will be one region to the left tail. It'll be a left tail on the graph, on the PDF graph, and it'll be one region there that we have an area of. And the area of that region under the PDF is 0.1, which is our alpha. So in other words, the probability that t is less than the critical value c should be alpha, or 0.1. Now, since the t statistics in this case have a t distribution with 9 degrees of freedom, remember that's one less than the sample size, we can compute c using an inverse t function. So c is inverse t of 0.1 comma 9, and that equals negative 1.38 something. Here it is on the calculator. In the newer calculators on the TI-84s, you would say it'd be distributions. So you go second vars would be distribution, and then you choose, I think it's like maybe the fourth one down or something, or maybe a little bit lower, but it's inverse t. So you choose that one. The newer calculators, it'll ask you for area and degrees of freedom. Area means the area under the PDF curve to the left of the x value or c value that we're looking for. And the area to the left is 0.1, and it's 9 degrees of freedom. We paste that in. In the older calculator, this screen doesn't show up, but you just type it in straight away like this. Just got to remember the order. The first number is the probability to the left. The second number is degrees of freedom. Boom, there's your critical value. So it's that easy to compute a critical value. Now we'll make our decision in just a minute by comparing t star to the c value. The other way we can do it is what's called the p-value method, which personally I like a little better. So remember, what is a p-value? Well, in general, a p-value is the probability of getting a test statistic of the particular value that we got, or something that's more extreme, given that the null hypothesis is true. So more extreme in this case means further to the left, so something at the level we got or left. So, well, what are we doing? We're just seeing that, we're just finding the probability to the left of this t value. So that's a t-CDF from negative infinity up to whatever t star is within -1 degrees of freedom. And this, we know that in a t distribution we can use, instead of negative infinity, usually you can use negative 100, that should say, as a replacement for negative infinity. And we've done this many times before, but of course it's not that there's not any probability or area under the PDF to the left of negative 100. There is something there, but the point is that it's so small to be of no practical difference, because it would only affect digits that wouldn't show up on your calculator anyway. So this makes so the negative 100 is usually far enough out that it doesn't really affect anything except maybe the last digit or so here, but it basically doesn't affect the digits here. The t star is our test statistic there, and our n-1 is our degrees of freedom, which is 9. So here's the calculator screen, at least for TI-84, right here. Since I'd stored this as t, I could just go t-CDF negative 100 comma t comma 9 and save myself a little typing of all these digits again, since I saved it earlier. But anyway, there's a p-value. Now we're going to compare p to alpha to make our conclusion. So let's make our conclusions now. In the critical value method, we're comparing test statistic to critical value. That basically is a t value to a t value, or an x to an x on the distribution of these t scores. Okay, so compute the test statistic. Compare the test statistic t star, which is negative 1.59, to the critical value negative 1.38. Notice that negative 1.59 is less than negative 1.38, so t star is less than c. Since it's a left-tailed test, that puts the test statistic in the critical region. So if it's in the critical region, we reject the null hypothesis in favor of the alternative hypothesis. If we do it with the p-value method, we're comparing the p-value, which turned out to round off to be 0.07, to the alpha value of 0.10. The 7% is less than the 10%, or 0.07 less than 0.1, so p is less than alpha. Anytime p is less than alpha, we reject the null hypothesis in favor of the alternative hypothesis. So, note that we can use either the critical value method or the p-value method, and we reach the same conclusion that we're going to reject the null hypothesis. Now, when you're reporting this, it's typically much better to report the p-value, because you can look at this with a p-value of 0.07. If somebody used a different alpha value, like a lot of people like to use 5% or 0.05 for alpha. If it was an alpha 0.05, then our conclusion would be completely different, right? Because the p would be greater than alpha. So this is not really strong evidence that the students got less sleep, but there is enough evidence at the 0.1 level to reject a null hypothesis, but not enough evidence at the 0.05 level. And just reporting the p-value does that. Now let's illustrate what's going on here with the pictures here. And so what we have here graphed is the same graph twice. It's the graph of this t-distribution with 9 degrees of freedom. Notice that it's mound shaped, kind of bell shaped, kind of like the normal curve. It's centered up at 0, but it's a little bit wider, a little bit more spread out, a little bit bigger standard deviation than the normal curve. Okay? We can see all these numbers that we just did somehow or another on this figure. So let's first look at the top graph. On the top graph, we illustrate in red the critical region, and the red area is equal to the probability that x is less than this critical value, c, and that's going to be our alpha level. So the red is alpha. Now we compute the critical value, which is the boundary of this red region, and that was a negative 1.38 something. So that's the boundary right there. That's the C value. Everything to the left of that is the critical region. Down here we have the boundary of this region down here is your test statistic T star. So T star is negative 1.58 something. That's the boundary value right here. Anything to the left of that is shaded blue. And so that blue area is actually the equivalent to the p-value. So there we go. So what can we do? In the critical value method, we compare where the T star statistic is to the C. In this case, it's to the left of C. That puts it in the red region, the critical region. And anytime you're in the critical region, we reject the null hypothesis. If it had been over here in the white region, then we would have not rejected the null hypothesis. The p-value method, then we're just comparing areas to areas here, or probabilities to probabilities, and notice that the p probability of 0.07 is less than the probability up here at 0.1. So this blue area is smaller than the red one. So this blue area down here at the bottom is the p-value. The red one up here on the top is the alpha value. And so anytime you get p less than alpha, that's when you reject the null hypothesis. So you can see the pictures there. So let's state and interpret the conclusion in the context of the problem. So here's how I would state this. And notice that really to state your answer, you need at least a sentence, maybe a couple of sentences to state the answer. So here we go. The mean amount of sleep for the students in the sample was 6.5 hours per night. This results in a p-value of 0.0735 from a one-sample left-tailed t-test. So at the alpha equals 0.1 level of significance, we see that there is sufficient evidence to conclude that the average amount of sleep for all students at this university is less than the hypothesized 7 hours of sleep per night. So note that in our conclusion, we included the sample mean, the hypothesized mean, the p-value, the alpha value, the type of test, and our conclusion stated in the context of the problem. Now in the next video we're going to show how we can use the built-in apps and the calculators to go ahead and find this, and we'll probably go ahead and work out this particular example in it as well using a calculator shortcut.